I'm Sacha Krstulović. I'm the VP of Technology at Audio Analytic. Thank you very much for the invitation to talk in this workshop, and again, thanks a lot to the organizers of the workshop, Mark, Thomas, the whole team, and everyone else who participated. I think this kind of workshop is actually, there is something really important happening in this kind of workshop, is that it's participating to consolidating the community around that topic of sound recognition, which is not speech, not music, but all the other sounds. To give you an example of what I mean, I come from a speech background, and then probably 15 years ago, there were not that many people talking about expressive speech, for example. And then they started to talk to each other and go, oh yeah, we're doing expressive speech as a side topic to speech in general. And then they started making their own workshops and started making European projects and research networks. And at some point, that was probably about 10 years ago, there was this European network called Humane, which really formalized a framework for research in what was called at the time affective computing and expressive speech. I think we're still at a stage where this thing is starting to happen. Most of us were doing sound recognition as a side of this and that, as a side of being a chip manufacturer looking for new topics for new applications of the technology, or as speech people getting interested in other sounds than speech, and so on. And so this kind of workshop participates to putting the whole community together. Within the first hour of the workshop, we were already having some scientific debate. So now for the rest of the day, every time someone's going to say MFCC, they're going to go MFCC. Anyway. We had also things like lots of talking about neural networks. Oh, I can't say that my system is better than neural networks. One thing that we're seeing in this workshop, which is really nice and really important and really interesting, is the diversity of systems which are being showcased and which have been explored as part of the DCASE challenge. And I think today we're having a workshop. Maybe in a few years we're going to have maybe a conference or maybe something like that. So thanks again to the organizers, to Thomas, Mark, Anna Maria, Tony, and everyone who participated in this, because this is really, really important in terms of making a community of sound researchers. Now, I come from the industrial side of that question. So at Audio Analytic, what we're doing is we're commercializing automatic environmental sound recognition for the smart home. We like to call it sound recognition because it makes it sound a bit more intelligent than sound detection. So I think one of the things the community is still looking for is a terminology, is what it is that we're going to call these things that we're doing. At Audio Analytic, we like to call it automatic environmental sound recognition. So we're recognizing every sound which is not speech, not music. So in the community we know that as audio events detection. I'm not going to focus this talk too much on scene detection. We can do that, but that's not the bulk of our commercial activity. Our flagship sound sensors, we call them, are currently baby cry, smoke alarm, and glass break. The storyline of this talk is going to be about how you go from research, from your algorithms, your neural networks, your MFCCs, sorry, and so on, down to impact, down to something which is an application and has some kind of use for someone, or something that someone is willing to buy. Before the research, we all understand that we need some data, so I'm going to talk a little bit about that. We all understand that we need some evaluation methods, and I'm going to distinguish two types of evaluation. So lab evaluation, but also field evaluation, which can be slightly different from lab evaluation. Again, I'm going to say more about these things. There is one thing which I didn't put in this slide, which is also very important in terms of impact, but which is not a technical thing, which is you also need a sales team, a marketing team. If you're going to want to sell your technology, you're going to need to be strong on these things as well. So I want to pay a little tribute to the sales and marketing teams at Audio Analytic, who are working as hard, believe me, as the engineering teams to make these useful and to make it accessible for the wider public. Now, one interesting thing is it that the applications can inform the research topics and inform the methodology about sound recognition? And that's going to be the storyline of this talk. So if we focus first on the applications and impact, what do we mean application impact? In the case of audio analytic market and applications, we are focusing primarily on the smart home market. So we run on products like this. So this is a set of Swan cameras. Swan is a brand of DIY security. You buy your box with your cameras, you screw them at home yourself, you hook them to the Wi-Fi, and those cameras, and then you have a whole web backend where you can look at your home when you're not at home and so on. And they were interested in these cameras being able to flag special events. And I'm going to tell you a bit more about that. This is another type of surveillance camera. It's a brand called MyFox in Europe, and this is a smart bulb. So one of our customers is a Chinese company called Sengled. They make bulbs with extra functionality in the bulb, and in that case, this bulb has a whole audio acoustic subsystem in the bulb. This grill here, it has loudspeakers. It can play back music via Bluetooth, but it also has microphones, and it's able to react to voice commands. And then they were interested in can we put extra functionality related to sound detection in that bulb to make this bulb, to give this bulb a richer set of functions. One thing which is really interesting, and which is a significant sign of this market growing, is that this is supported by distributors. In the UK, it's Dixon's, PC World. There is a brand called Maplin as well. In Germany, that would be Saturn. In France, that would be Darty. In the UK, that would be Costco. So all these people who sell consumer electronics and white goods, once they've sold all their washing machines, all their TVs, all their PCs, laptops, what else do they want to sell? Well, if you go to a Maplin store nowadays in the UK, you're going to have a new section called Smart Home Products, where you're going to see some of these cameras, connected devices, Internet of Things systems, and that is a sign that these things are really catching commercially, and this is really a booming market. We foresee that millions of devices will be running in people's homes by 2020. So the application behind that is, so we call it also acoustic ambient artificial intelligence. So ambient because it's everywhere. It's just like the network or the internet is kind of like around you. It does something around you. You don't see it, but it does something around you. Acoustic because it's related to sound recognition. Artificial intelligence because we want to emulate a human function of hearing sounds, but with machines which are going to do that for you when you're not at home. So essentially, the very simple application is your home listens for audio events and alerts you or takes appropriate actions. Whether you're in the home or out of the home doesn't make a difference. The home does that for you. It has ears. It hears what's going on. One of the values behind that, it's not the only one, but one of the values is peace of mind. You go away from your home. Is your home on fire? You don't know. But if you have a system which is able to listen to the sound of smoke alarm, then you can receive an alert. Oh my God, my home is on fire. Shall I call my neighbor and so on? So that's peace of mind of your home taking care of its own surveillance. Are there any other markets and applications? So we've had chats with many researchers asking, but what about smart cities? What about elderly care, that kind of thing? So there might be some realization in the market of these type of applications, but they didn't appear at the time where we were doing all our market and business analysis, they didn't appear as powerful as the smart home market. So at the moment, really the big wave, the big growth is coming from the smart home market. Therefore, that's what at Audio Analytic we chose to focus on, at least for the time being, for the moment. Now, getting back to the storyline, so how do these things inform, for example, the type of data we want to work with? Well, at a very simple level, when we started working with Mark Plumley on sound recognition, on various collaborative projects, we realized that there was no public database for indoor sounds. Most of the public databases for public research, shared amongst researchers and so on, were outdoor sounds, were recorded with people walking in the street with a microphone. And then we were like, we had that kind of slapping on the forehead moment, like, oh my gosh, we need an indoor sounds database to build collaborative projects and to focus the research on that particular domain. Working on indoor sounds does not reduce the generality of the sound recognition problem. The taxonomy of sounds is still generic. You still have a variety of sounds. I'm going to talk about it more in the next slide. But that might help focusing the research on something which is a bit less generic than trying to tackle all the sounds in the universe. Suddenly you're focusing, okay, I want to study sound recognition, but I'm going to restrict it to one possible application so that I don't try to solve the whole generality of sounds. Maybe by focusing the research is going to help achieving some outcomes faster than trying to take the whole generality of the problem. When I say taxonomy of sounds, I mean this. So in a home, you might have sounds like this one. That's a smoke alarm. It's a very simple beep structure. Okay, you see in your spectrogram you have pure tones. You might have something like this. Oops, no, not this one. Come back. So that's a baby cry. That's a vocal signal, but of a particular kind. It's not speech, but it's still produced by a vocal tract, a small vocal tract, but a vocal tract. You have things like this one. That's a glass break. That's a percussive sound. And this one, that's a vacuum cleaner. And it's got that kind of shape noise characteristic. And at the same time, that hiss in the middle. All these things result from different production processes. And whereby speech is limited by the production, is bounded, not limited, is bounded by the fact that it's produced by a human vocal tract, or whereby most of musical instruments are based on some form of resonance process. You have things like the glass break, which is a percussive sound. I haven't seen much literature about recognition of percussive sounds. Percussive sounds which would not be musical instruments, or shape noise like the vacuum cleaner. Again, that's a kind of thing which is neither speech nor music at a very, very deep level. So that's one thing which is very interesting to keep in mind when doing research, for example, on features. Would acoustic features, so MFCCs again is the debate, but would the speech-derived features work for all these things? Do you need different features for different sounds? That's a very interesting research topic. I would still say that MFCCs apply to most of these things, but let's have this debate some other day. Right. One thing about data which we've talked about, we've heard mentions of in this workshop is the labeling. Labeling is necessary. You need to know where your sounds are in order to be able to train any machine learning system, because the task of the machine learning is to associate the semantic labels to the audio. So we need the semantic labels, and we need humans to distribute those semantic labels. So that's very labor intensive, that's very costly. As soon as you grow the size of your database, then it costs you a lot to label. And that's one of the limiting factors in the type of research that we're doing. But it must be done. We cannot not have labels. And it must be done well, because if you have labeling mistakes, then your system is gonna learn the wrong thing, and you might have limitations in your errors, which are not limitations of the system itself, but which are limitations of the quality of the labeling. So what about studying cost reduction strategies? That could be also possibly an interesting research topic. You're all familiar probably with semi-supervised or unsupervised learning. Sorry, just one thing before that. So what we call the bucketing approach is the labeling approach, which was used for task 4 of the DCASE challenge. As you know from Mark, so we built we advised on the labeling of this data set. And one of the strategies to reduce the cost of labeling was, instead of locating the boundaries very precisely in your audio, we just divided it in 4-second chunks and then asked the listeners to tell us what is in this audio. So instead of having to do a very minute work of locating the boundaries, they just say, okay, in that 4 seconds I hear male, female, child. And that can have two functions. So it's a form of kind of weak labeling or impure labeling, but it can also use as post-processing before you actually locate your more precise labels, because that way, for example, you can remove all the silence parts, or you could have some specialized labelers for particular types of sound. So it's an interesting way of reducing the cost of labeling, albeit it's not delivering the same purity of data as if you locate your boundaries very precisely. Now, The second thing, so semi-supervised and unsupervised approaches are possible for labeling data. They will still require some human checking and or hand correction. So when you have supervised labeling, you tell your system where are the crosses, where are the circles. When you have unsupervised labeling, you let your system find the clusters, but at some point you still need a human to tell this cluster is crosses, this cluster is circles. And you could use semi-supervised approaches where you label a proportion of your data, you throw the rest at your system, and then you refine your labeling that kind of way. Again, we haven't seen a lot of literature on that for sound recognition, but that could be a very interesting research topic and something that would really solve some of the very concrete problems we have in this type of research. In terms of data collection, what we've done at Audio Analytics, so this is an example of what we've been through in the early days of the company. We bought every single smoke alarm available in the UK and in the US. There is an interesting story about that, is that some smoke detectors work by ionizing the gases, and in order to ionize, they need an electronic component which has a small dose of radioactive material into it. Imagine the hassle of shipping radioactive material from the US to the UK. It's been fun, but we managed. And we located these smoke alarms in real environments in a variety of homes with various room responses and so on. And we recorded all of that, and we have this huge, probably the biggest database in the world of smoke alarm sound recordings in real locations. And believe me, those things can be different from a simulation. So devil is in the detail. And we have explored all that kind of detail. This is when we did the data collection for glass breaks. So when I'm not wearing a suit, I'm actually wearing overalls and a helmet. This is an old decommissioned military hangar in a place called Alconbury in the UK. That's where they used to do the acoustic test of airplane engines. And it's entirely lined up with non-reflective material, so it's almost anechoic, almost perfectly anechoic. And so we've hired that place, and then we've been having fun breaking windows. And again, breaking windows in the whole generality of breaking window, that is, we broke, so this is an example where we're breaking a glass sheet, but we also broke real windows with all the effects associated with the frame and so on. So we broke real windows in order to explore and analyze how it sounds like and have some real training material, not stuff that we harvested from the internet randomly. This was really real and recorded through a proportion of target device, an array of different consumer devices. I'll come back to the consumer devices in a minute. So that was about the data. Going on about like how the applications and impact can inform the research. So this is a series of recordings from 9 different consumer electronic devices, off-the-shelf ones, like real ones.
Yeah, so, well, 2 years, I guess.
Where's my mouse?
Yeah, so, well, 2 years, I guess. 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 Yeah, so, well, 2 years, I guess.
So you can clearly hear that all these devices, all the channels had very variety of channel responses. Some of them even had noise, like the last one has this hiss in the middle of the spectrogram. And this is reality. We can't consider that every sound recording is going to be made with a high quality, recorder, Tascam or whatever, Shure microphone with 48 kilohertz. This is the reality of what the system is going to run on. So we need to cope with that. So research topic, robustness. There was a whole era in speech where people were working on robustness. So we need that to happen in sound recognition as well. I mean, we have our own approaches to that at Audio Analytic, but again, what I'm trying to convey here is that these things it would be nice if we had more friends working on that with us. Meta parameters, so optimization, whatever the machine, be it the DNN, a Gaussian cluster, and so on, you're going to need to optimize the number of layers, the parameters, how many Gaussians, what are your learning rates, what is your feature set, and so on. And so machine learning being actually way more complicated than human hearing, there is quite a lot of things that you need to tune. in order to be doing a good job in tuning all these things, in order to be able to automate this kind of optimization, you need to pay attention to your evaluation metrics. And evaluation metrics are again something that we've talked a lot about in this workshop. So lab evaluation is what I mean by this, is looking at the evaluation metrics in the lab. Once you have your offline recordings, you want to look at some evaluation metrics. We've seen a lot of use of precision recall and F-score. You're all familiar with this. One problem with the precision recall and F-score is that those things are dependent on the data set size and the priors on your data. If you double the size of your true negatives, without changing anything to your system, you're going to change something to your precision recall and F-score numbers. And that's a bit concerning, because then those numbers are tied to the data set that you're using to calculate them. In practical reality, non-targets are actually very important in the sense that we don't necessarily have a closed set of imposters, of adverse sounds that are being thrown at the system. The system is continuously exposed to target sounds. So how can you calculate this false positive, these rates when you have an infinite probability that something else than your target sound is going to happen? That's a very interesting question to ask as well. So to give you an idea what I mean, in the clear evaluation in 2006, the confusion matrix was 13 classes against 13 other classes. So you would have things like, I don't know, the hand claps are being confused with the door slams, but not so much with the speech. DCASE, 2013, there was a bit more progress in more classes. But actually what happens in the reality of a practical sound recognition event, which is listening 24/7, is that you have one sound that you're trying to recognize, say smoke alarm, against an infinity of sounds, almost infinity of sounds, which are going to get thrown in the system. It might be possible to enumerate all the sounds which are happening in a home, but that's going to be a very, very, very big set. So you're not going to have a confusion matrix like this. You're going to have a sort of confusion vector with one sound against the rest of the world. While true positive units are easy to define, so for example, we all know what a smoke alarm is, we all know what a baby cry is, although there is variation in that, and you might discuss, do you include in a baby cry the baby happy sounds or not? So, well, there is still a concept of what your target sound is, therefore your event is fairly easy to define. There is going to be some consensus, yeah, this is a baby cry, this is a smoke alarm. Now, what are the false positive units? If you want to compute precision recall F-score, then you need to count something. And so what is it that you're going to count as false positive units? So you could use block-based metrics. We can call them blocks or chunks depending on the articles. So that was introduced by Tony and Thomas and all the team in Finland. There are pros and cons of that. It works if you divide your data, your whole non-target data into chunks and then use that as your false positive units. But it's got some limitations. I mean, we've seen that some of the error rates were becoming different depending on whether you were looking at events or whether you were looking at blocks or segments or whatever you call them. So tackling these questions in evaluation is really, really, really important. There is another pitfall with the precision recall and F-score, is that those measures come after the decision that you've made on classification. Most classification systems work by thresholding some form of score. If it's a DNN, it's going to be your class membership probability. If it's a GMM, it's going to be the likelihood. If you negate the likelihood, you can have something which is like a similarity score, where you want your score to be small if the distance between your sound and your model is small, large if your distance between your model and score is large. Most of these machines, for SVMs, you could use a deviation from the margin. Most of these machines are able to emit some form of score, and the classification process or recognition process is about finding where you're going to put your threshold to say, aha, this is my target sound because the score is going under a certain threshold. This is the notion of the decision. At some point, you need your system to make a decision about the sounds, not just giving you a likelihood or a membership probability or something like that. The given choice of threshold defines a single operation point. So the operation point is a compromise that you make between false alarm and misdetection rates. You could make your system more conservative. If you put your threshold way down, you are going to let through less of your audio events. but maybe in that case your system makes less false positives, but then it's also going to miss more of your true detections. Conversely, you could make your system more sensitive, more permissive. You let through more things, you put your threshold higher, more things go through. It might be better at doing true positives, but then you might also increase your false positive rates by doing that. So you always kind of like having that kind of choice to make. If you're application dependent, you have that choice to make where do you want your operation point. But what we really want to evaluate, is it the wisdom of choice of the threshold, or is it actually the power, the modeling power of our models? So what we want to evaluate is really the models independently of that operator action, which is choosing the operation point. There is a tool for that, which is the detection error trade-off, dead curves. And those things are plotting the whole range. If you were browsing your threshold, the whole range of your threshold, that would be browsing the whole range of operation points that you can have for a given system. So if you set your system to be conservative, for example, you could be sitting at this point along the dead curve where you have a very low false alarm probability, very high false alarm probability, but a very high rate of misdetections because your system is conservative. If you alleviate the threshold, if you move it, you're going to move along the dead curve, and then you can end up having at some point a system which is very permissive, which is not doing a lot of misdetection, but which would have a very low false alarm probability. So dead curves allow to compare the systems independently of the setting of the operation point, and that's a very interesting concept. So this is a comparison of three systems, random system ABC, where the purple one is clearly doing a better job across the whole range of operation points than the blue system. If you want to summarize the dead curves to one figure, you can use the equal error rate, which is actually the intersection of the diagonal with the dead curve, and that gives you one figure, which is fairly convenient to summarize your whole curve into one number, under the assumption that the dead curves don't cross. Lots of work on these things has been done in the domain of speaker recognition. There is a very interesting article from David Van Leuven and Nico Brummer from 2007. The article is called An Introduction to Application-Independent Evaluation of Speaker Recognition Systems. So application-independent evaluation, that's really, really interesting. And it's actually a chapter in a book from the Springer series, Lecture Notes in Computer Science. I would encourage all of you to read that. It's really fascinating. Now, what happens in that kind of case? If you have a customer who wants to minimize false alarms in order to minimize support requests, because it so happens that people don't like to get false alarms. And if your deaths happen to be crossing, and believe me, those things happen in real life, suddenly you have, for some systems, you have dead curves crossing. Which one do you choose? Do you base your decision on equal error rate, in which case you would choose the blue system, or do you use something else? And there is a thing called the decision cost function, which introduces a cost for misdetection and false alarms, and also introduces the probability of your target sounds happening. And that was already a step, an extra step in the decision and in evaluating the system, which is maybe you want to pick your operation point at the DCF, not at the equal error rate. And that in turn is going to change your perception of which system is the best. So in speaker recognition, the values for the cost functions were set to 10 for a miss, 1 for a false alarm. So they were more concerned about missing access calls than about and so on. We still have some work to do to decide what are the best parameters in sound recognition. It might also be application dependent and so on. Also, one of the problems is that the probability of the target sound for sound recognition could be infinitely low in real life. What's the probability that your smoke alarm is going to sound compared to the probability of everything else happening in your home, speech in particular, other sounds related to human activity? That's a very interesting thing to think about. For a commercially deployed system, the relevant metrics are the following. They are so the true positive rate is still valid. Everyone agrees on what's a baby cry or what's a smoke alarm. So that's fine. Out of 100 baby cries, X were detected. But the false positive rates have to be expressed per time unit. What customers want is no more than X false alarms per year. And this concept of across some length of audio exposure, some false alarms are going to happen. This is what we're interested in from a commercial perspective. That's what's going to convince the customer that the system actually works if it does no more than X false alarms per year. That's because behind all that, errors translate into user experience. And what we need to do at Audio Analytic is to evaluate end-to-end user experience, not just the machine learning error rates, but what the error rates translate into in terms of people being happy about what the system does, in terms of usefulness of the system. That's things we do routinely. We do have to mind not just a number, 70%, but how this number translates into something usable and something that people are going to be happy to use and happy to have in their home. Just a kind of parenthesis before we come back to user experience. Classification performance is not the only metric we might be interested in terms of performance. That's the results of a study we've done with Mark in a collaborative project which was financed by Innovate UK. We took a subset of the audio analytic data. We compared the classification performance of various types of machines, but in relation to their computational cost. And this is not the computational complexity. This is really, we counted the number of mathematical operations that each and every of these models were doing. And so the results are this. So the GMMs were doing a good job in classification performance at a low number of operations. Neural networks were really performing well in both the classification performance and the number of operations. The support vector machines were all over the place. They could be in certain cases good in classification performance, but their computational cost was way too high for example, embedded systems. And that generalized for both the baby cry models and the smoke alarm models. So I'm not a big fan of saying that DNNs are the best thing in the universe, but in that case, they clearly outperform the GMMs and the support vector machines. Now, to the defense of GMMs, these were not trained with discriminative training, so it could be the case that actually it's not about the machine, it's about the ability to discriminate. But those are, again, scientific debates that we can have and scientific research that we can get going. But the point here was, okay, we want to know about performance, but we also want to know at what cost you get that performance. That's very important for industrial applications. Why is computational cost important? Well, our system runs on the edge. It runs on embedded devices which have tens of MIPS available only and hundreds of kilobytes of memory available. If you got 2 megabytes of memory, then you're a lucky happy chap. So some of you will ask, but why not using a PC or why not running on the cloud? Well, PCs are way too expensive for consumer devices. There is a notion of the bill of materials, what you put in your device to achieve a certain market cost. PC chips are just simply too expensive. There are questions of form factors. You want your device to be a small thing, not a big cupboard, okay, so that it's going to sit nicely on your coffee table and so on. There is a very important question about privacy. People don't want their audio to go out of the home. Most speech recognition system, people are in control of what they're going to send to the cloud. You press your listen button, your Siri button when you want something to be translated. In the case of a sound recognition system which is going to listen 24/7, people really don't want that to go out of the home. And then there is a question of reliability. If you run on the edge, you don't depend on connectivity, so you still depend on internet connectivity to send you alerts, but at least the system can buffer them until the online connectivity comes back if the online connectivity gets recorded. So there is a question of reliability. Continuing with the qualitative assessment. So dead curves give you an equal error rate, and DCFs give you some measure of performance at some operation point, but they don't tell you what the errors actually are. And let's take a toy example. Assume a test database. This is really just random numbers, but like you record 100 homes with a false alarm rate of 20% on, say, detecting baby cry sounds. And then you have this dog, which is crying like a baby and happens to generate 90% of the false alarms from a single home. meaning that the remaining 99% of homes share only 2% of the false alarms. If you ignored this dog or this single home, then your FR rate would fall to 2%. Is that a bad system or is that a good system? Okay. So there is a question of qualitative assessment. Some of the errors, maybe the 70% error rate that we get on some of these tasks, maybe that's hitting some of the limitations of the data itself. Maybe that's hitting that kind of limitation. So again, dead curves and equal errors give you a rate, but they don't tell you what specifically needs to be addressed to make the system better. So in that toy example, if we were addressing dog versus baby cry confusion, then we would solve most of the errors. That gives a face to the enemy. It's like you know that your biggest problem is that. But beware of what's called horses. There is a researcher called Bob Sturm who has done a series of articles about what he calls horses in music recognition. And it's the paradigm that the system may not be doing what you think it does. Why it's called a horse? Because this is an image of Hans the horse. The story about Hans the horse is it's a horse that people believe could do mathematics. You could ask the horse how much is 2 plus 2. The horse would tap his hoof 4 times and people were like, oh my God, the horse is doing mathematics. It can do additions and so on. And actually, after some scientific research by this bearded guy in a lab coat, he found out that the horse was actually latching on people's reactions to the horse's reactions. So people were getting excited the closer the horse was going to the solution. Humans were sort of getting, and then the horse was picking that and actually picking only that. So whereas people were thinking the horse was doing mathematics, the horse was actually very good at doing people's behavior, picking people's behavior. And those things, again, happen in sound recognition. One of the articles of Bob was analyzing systems which were claiming to do genre recognition. And then he proved by taking the database which was used for this work and messing with the tempo of the beats, of the tracks, that the system was actually doing tempo recognition, not genre recognition. So we have to be really, really careful about the claims about sound recognition, because again, if we are not very cautious with the methodology, with the data sets, it might be that the system, the machine learning system, just latches on something which was the microphone or something like that, rather than latching on the sound themselves. So this is really important to keep that horse paradigm in mind. And again, are all the errors equal? If it's the dog, if it cries like a baby, is it a false alarm? Is it not a false alarm? Is it perceptually far enough so that you want to consider it still a false positive, or is it a kind of legit mistake of the system? What if a vacuum cleaner was triggering baby cry false alarms? Now that would be a bit more serious. Maybe that would piss off your customers a bit more than if it's something that they can say, oh yeah, it's just a dog. Yeah. Field evaluation. So you have your lab experiments, you've done your equal error rates, you've done your error analysis. What else do you want to do? Well, you want to actually put your system in the field and really try it against reality. You can't just leave it at a lab evaluation, because this system will end up in people's homes, so you have to make sure it's working as it says on the tin. We have a tool for that. At Audio, we developed that thing called the Polo, Prototype of Listening Object, which is an end-to-end testing platform. We are not a hardware company, so that's not something we sell. So this is not a product. This is really a test platform. It's the user interface is made of Python. The hardware is off-the-shelf hardware. It's a Raspberry Pi with a bunch of off-the-shelf screens, modules, microphones, and so on. And the functionality it offers, the functionality it implements, is this. It's running our sound recognition software, and when it's got a microphone, it's doing the sound recognition, but on top of just the sound recognition, it's packaging the alerts, sound recognition alerts, into an email, and it sends the email to the recipient. Because it's email, now everyone has email in their phone, the people can look at these alerts in their phone, and inside the email you have an audio clip of what has been detected, so people can actually verify the alert. And that is an instantiation of some end-to-end user experience of sound recognition, whereby people, you don't leave it at just my system recognize sound. You just give the whole power to people to look at what the alerts were and form a human judgment about, oh, I'm happy about this alert, I'm not happy about this one, and so on. So in terms of evaluation of the system, you're not just evaluating error rates, you're evaluating the whole chain and the whole experience of sound recognition. This Polo is available to research partner under contractual agreements. If you're interested in using that, we're not going to give you our sound recognizer, but we can discuss lending you the whole shell around it, so the whole user interface and alerting system, because we think that we should foster the actual testing of these systems in real life, because equal error rates or performance recognition rates are not enough to give an idea of is the system useful. So again, so the goal is really to enable field testing of, in that case, our sound recognition software. So with that, we can measure actual true positives and false alarms per time in the field across a sample of representative homes. There again, there is a bit of design of experiment to do, because different homes with different occupancy generate different types of noise. If you have people with children, they're going to make certain type of noise. Maybe if you have senior citizens, they're going to listen to their TV louder. If you have someone with a dog, you're going to have dog sounds. If you have the odd guitar player, you're going to have music sounds. Some people are living close to construction sites. Some people live close to airports. So all of these things need to be sampled. You can't sample all the houses in the universe, but you need to make a good job of sampling the whole diversity of the audio landscapes that might happen in a home, in order to have a true forecast of how your system is going to perform in the field. And also something really important is, as I said before, to measure the user experience. You could use methodologies such as opinion scores, which are things used in speech synthesis, where you ask people a rate on a scale of 1 to 5, and then you ask a precise question. So can you understand this alert? Do you know, do you have a concept of why the system sent you this alert? Or is this alert annoying? Is it useful? Is it not useful? You can measure a bunch of things like that with opinion scoring in order to form an idea of user experience. Is the system desirable, accessible? Do people understand it? Is it credible? Do they believe that it's doing what it says on the tin? Is it valuable, findable? Is it more like how do they understand how to use it, and so on? Right, so this is the conclusion of this talk. I hope I'm on time. Walking along that path of pathways to impact, things which are interesting to look at. So in the case of data, indoors data might help to focus the research on something which is a particular subset of research without reducing the generality of the research. Taxonomy of sounds is important to keep in mind, because differently from speech and music, we're not as bounded as speech and music. There is a whole bunch of types of sound, a whole variety of types of sound which is different. Reducing the cost of labeling is an interesting thing to look at. When it comes to research, when I say research, I mean algorithms, machine learning, and so on. Of course, we want to research machine learning and acoustic features. That goes without saying. But also giving a bit of attention to robustness, giving a bit of attention to optimization of meta parameters. I didn't talk a lot about that, but there are some approaches like Spearmint, like things like which are trying to draw density functions on the parameters of, on the meta parameters of systems. So there's a whole field of research there, which is really interesting as well. Lab evaluation, so decision, how do you actually make the decision from your likelihood score or from your network output? It's not necessarily as straightforward as just making the output of your networks compete. You might want to weight your outputs and so on. So decision, how do you decision? Is there more interesting things you can do on your score, some form of post-processing to actually improve from your equal error rate at the decision level? That's a really interesting thing to think about. Keeping in mind that there is going to be infinite false alarm priors, and that you might want to use a false alarm rate per time unit instead of a raw false alarm rate is something interesting to keep in mind. Qualitative error analysis, what is your system actually doing? What type of errors is it doing? If you have 30%, is it 30% of the same error? Is it 30% of the variety of errors? How does that inform you on the next stage of your research? Performance versus computational cost for us in the industry is very important, because we run on embedded devices. Don't take PCs for granted, don't take the cloud for granted, because there is a whole bunch of impacts of useful applications which cannot use a PC, cannot use the cloud. And in terms of field evaluation, I would encourage everyone to try once to take their neural network, their NMF, whatever, put it in a 24/7 system and see what comes out. and it can be surprising. And then also measuring user experience, what we really want to optimize at the end of the day. If we want that research to be useful, what we really want to optimize is the user experience. We want people to think that this is useful. And so optimizing the error rates is a milestone along the way. It's useful, it brings you somewhere, but it doesn't bring you the whole way down to user experience. Thank you very much. That's the end of the talk. If you're looking for a job, talk to us as well. Thank you very much.